Close enough. So, once again, we're going to try to put the lectures online. I sent an email out with links to the lecture from Friday via Blackboard. Eventually, I hope to put it directly on Blackboard. But until we figure that out, it's not as easy as we thought. We're just going to put them on a unadvertised YouTube site that you can only get there if you have the link. And so I'll send the links out, that way you guys can get it and you don't have to worry about any kind of copyright with SDSU for now. But eventually I want to figure out how to put it directly on Blackboard. The problem is the files are currently too big. So that's from that perspective. I think we have 6 lectures until our test. So our test is not next Saturday. It's the Saturday after that, so about 2 weeks until the next exam too. That will be in a different room. I'll let you guys know on Blackboard and that room. I did find out apparently that Saturday is Future Aztecs Day, or Explore SDSU Day, whatever they call it now. So we had to get a different classroom because the normal room was being used for that. So there will be a review session. We have the same room booked as last time, which means we're going to do what we did last time and just probably go to that bigger physics room we went to for the last review session. But we will have one at the same time in the same place. Some other question?
We can't find another class because that one.
Oh, the plan is that big one was open, right? The gymnasium-looking one was open.
The sound wasn't good.
I tried. It's not exactly as simple. We were lucky that that bigger one was open. So, on Friday we started talking about electrophilic aromatic substitution, and there are 5 electrophilic aromatic substitutions that we discussed, and they're in the notes. And I'll finish talking about them today. The 5 were halogenation, nitration, sulfonation, Friedel-Crafts alkylation, and then Friedel-Crafts acylation. And so on Friday we talked about 3 of the reactions. We talked about halogenation, we talked about nitration, and we talked about sulfonylation. And so just to give you guys a quick review for electrophilic aromatic substitution, the general trend in each mechanism of all these 5 mechanisms is identical. And the general trend is, we start off with an electrophile that I'm calling E. We use some sort of catalyst, whether it be sulfuric acid or a Lewis acid like FeX3. We take our electrophile and we go from being a normal electrophile to being an activated electrophile, i.e. E+. So we have to activate our electrophile for it to be able to react with the benzene ring, because remember the pi system from a benzene ring is going to be lower in energy than the pi system from a typical, let's say it's alkene, because of the aromatic stability. So we need much more reactive electrophiles for chemistry to work. So step 1 of the electrophilic aromatic substitution is going to almost be activation of our electrophile using a catalyst to give E+. And then once we activate the electrophile, then the mechanisms really collapse to be very similar from each specific reaction. Alright, so for example, if we have an E+, then the aromatic ring is going to attack, giving us our cationic intermediate. This is a fairly relatively unstable intermediate because it's no longer aromatic. And this is, this is the highest energy intermediate. And then because we want to regain aromaticity, some base, and the base is normally formed in the context of electrophilic activation. So when we activate the electrophile, in exchange for activating the electrophile, we usually form something that's a decently strong base for the chemistry at hand. And so then the base will now perform an E1 elimination, taking the proton and the carbon that the electrophile added to, and doing an E1 elimination to regenerate our electrophile. So I have an example, again with halogenation, particularly in the context of bromination. So Br2 is a fairly lousy electrophile, so we have to use a Lewis acid. So in this case, FeBr3. In general, your iron catalyst is going to be coordinated to the halide we use. So if you want to do a chlorination with Cl2, you use FeCl3. Bromination, FeBr3. So what happens is the Br2, and we went over this mechanism on Friday, so you guys should see this. The Br2 attacks the FeBr3, and eventually what we form is a bromine atom with a positive charge. So it lost its electrons in this activation. Again, the mechanism we went over Friday, and FeBr4. And so in this case, the FeBr4 minus is going to act as our base later on, and the Br plus is going to be our activated electrophile. And so now the aromatic system attacks the Br plus, giving us our cationic intermediate, and then the FeBr4 minus, and I do want the bromines pointing up, just to be more clear, that it's one of the electron density from the iron and the bromine. It doesn't matter which bromine, but the electron density is what is actually going to act as a base, and it's going to grab this proton, kicking off, doing the E1 elimination, giving us our product, and then the two byproducts are going to be FeBr3. So what happened was the FeBr4 donated one of its Br minus to act as a base to take a proton, making it FeBr3 again. And so, again, we, in essence, regenerated the FeBr3. So you only need sub-stoichiometric amounts, or catalytic amounts, of FeBr3 to activate it, because it regenerates itself in the presence of the mechanism. So FeBr3 is what we call a catalyst. So that gives us FeBr3, our product, and then when this bromine takes its proton, that's HBr. So review from Friday. The other reaction we talked about was nitration. All right, and in general, nitration is the addition of a nitro group under the action of H2SO4 and nitric acid to give us a nitroaromatic species. And so what happens is our nitric acid, HONO2 or HNO3, I just drew it out kind of phonetically. But our nitric acid is going to become protonated by the sulfuric acid to give us, and it can of course protonate each one of these oxygens. But remember, this chemistry, aqueous acid-base chemistry, is always in equilibrium. And in this class, when we're talking about equilibrium, I only want to see the productive pathway. By drawing your equilibrium arrows, you're acknowledging that there are other non-productive pathways that can happen. It's assumed. Just only worry about drawing the productive pathway. And realize these equilibrium arrows let you draw the productive pathway. And in acid-base chemistry, the productive pathway will almost always give us a good leaving group. All right? So do the protonation so it gives you a good leaving group. And your equilibrium arrows will let us know that you understand that a million things are happening, but there's only one or two productive pathways. So in this case, to get a good leaving group, we need to protonate this to give us an H2O plus. And then going from the H2O plus, this is a great leaving group. So it's going to leave, eventually giving us NO2. And in this case, NO2 plus is our activated electrophile. So it's our E plus. So what's going to happen is we form the NO2 plus just as before. The aromatic group's going to attack it. That's going to give us our cationic intermediate. All right. And then the base is going to come in. And in this case, there's two logical bases. Either water, right? Because this is done in, nitric acid is aqueous, sulfuric acid is aqueous. So this is an acidic water. This is acidic water. So there's definitely going to be some water around and act as a base. And that's probably the most desirable base. But you can also have HSO4 minus act as the base as well, because we do form HSO4 minus in this mechanism. and sulfuric acid is technically catalytic, but I'm just going to go H2O. It's going to act as a base, and it's going to do an E1 elimination to quench our carbocation and give us our product again. So the mechanism is very similar. It attacks the activated electrophile and E1 elimination to regenerate aromaticity. Yes?
So we don't want to make the nitrogen neutral, we just want to leave it as plus charge in the option.
Well, so this nitro group here, this is how you draw nitro groups. All right, so if you made the nitrogen neutral, then you have 2 oxygens with a minus charge. When you make the nitrogen positive,
what if you created a double bond with the oxygen that has a minus charge?
actually, you can't make this nitrogen neutral though, that's how I look at it. It's going to be really hard to make this nitro neutral without violating any chemical laws. So nitro groups are positive at the nitrogen with 1 oxygen with a minus and a double bond oxygen. That's just how they are. You're not going to be able to draw it in neutral. But that's fine. That's how nitro groups are. They are positive on the nitrogen. The other reaction I talked about real quickly was sulfonation. And in sulfonation, again, you take your aromatic group, and you take SO3, so sulfur with 3 carbonyl groups, and you throw in sulfuric acid. The activation for this is a very simple activation. Are you ready for it? Apparently this marker's not ready for it. It's just protonation of the SO3H to give SO3 with a hydrogen off one of the oxygens. All right? And so if you think of electronegativity, right, oxygen is more electronegative than sulfur. So this is just like an activated carbonyl to begin with. And so now that we protonate this and we have an S and an oxygen to positive charge, you can really draw a resonance structure where we now take this double bond and make it a single bond, where now our oxygen is neutral and our sulfur is positive. So what this means is, in a resonance hybrid, there's a lot of partial positive charge at the sulfur when we protonate the SO3H. There's a lot of partial positive charge. And so that means, since this is our E+, when this attacks, it's going to attack at the sulfur. Once again, to give us our cationic intermediate, gives us our cationic intermediate. And then we have water, or HSO4 minus, some kind of base. Go and do our E1 step to regenerate aromaticity and give us our sulfonylated product. Okay, and so once again, it's protonation followed by attack at the sulfur to give us our cationic intermediate, and then collapse to regenerate, E1 collapse to regenerate aromaticity. So those 3 mechanisms, it's all again acid, electrophile activation through an acidic mechanism, and then attack at the activated electrophile by the aromatic group to give a cationic intermediate. And then we do a quick E1 to regenerate aromaticity, which is really the driving force of this reaction. One thing I want to mention real quickly. One thing I want to mention real quickly about this chemistry is, so nitration, not reversible. Halogenation, not reversible. Sulfonation.
Yes.
Sulfonation at 100 degrees in aqueous sulfuric acid is reversible. And that's a useful thing to know, and I'll explain later on in this chapter why it's a useful thing to know. But for now, I just want to show you how it's reversible and why it's reversible. And I want you guys to remember, with sulfonation, not only can you put one on, you can take it off as well. And that is a useful thing to know. So you can take it off, and so the way you take off a sulfonic acid is you add aqueous dilute sulfuric acid and the key is aqueous dilute. Oh, and by the way, I should mention all the electrophilic aromatic substitutions I've shown you so far are done at room temperature or colder. So just assume all electrophilic aromatic substitutions are room temperature or colder. Yes?
So how come the second to last step, why doesn't it make SO3?
It can. Again, it's reversible, right? And it's just, it depends, the conditions will allow us to, so you're getting ahead because we talked in our office hours about this, right? So you're getting a step or two ahead. I haven't shown him how, but you're right, that intermediate does come into play. So let me go over it and then I can talk about it, okay? So you take aqueous dilute H2SO4, and instead of doing it at room temperature, you do it at 100 degrees Celsius. So you're boiling it in acid. That's harsh, right? You're boiling it in a really hot, very acidic medium. But under those conditions, what you get out is the desulfonylated product. So you took it off by boiling it. Instead of doing it at room temperature, like the Diddle mechanism, you just boil it in acid. And so the mechanism. So usually, so in this case, our quote-unquote electrophile is going to be the proton and sulfuric acid. And the way we're activating it is by heating it. So the first step is not all that different than an aromatic substitution. It's not. It is just 100 degrees with a very acidic thing. So 100 degrees is activating our proton as our electrophile. And again, there are going to be a million different non-reductive pathways. In theory, we could probably protonate each of these carbons, but none of them is going to give us a reductive pathway, so those non-reductive pathways will just go right back and give us the starting material. The reductive pathway is actually going to be protonation at the carbon adjacent to the sulfonyl group. So, in other words, protonating this carbon, so let me do the proton that's adding in green. So that gives us an intermediate just like this, right? And true or false, this intermediate is the same as this intermediate. True. So it froze as intermediate. The only difference is now, instead of being at room temperature, we're at 100 degrees. And so in a very equilibrium way, so our base can either take this proton or it can take this proton. And at room temperature, it does both. At room temperature, it does both. It does both at 100 degrees as well. But at 100 degrees, we get one thing, because we're at 100 degrees, that we don't get here. And that is the ability that since we're so hot, anything that's a little bit volatile is just going to boil away. It's just going to distill away. And so what happens in this case is water can grab this proton. So if it grabs this proton, it's just going to go back to the starting material. So if it grabs the green proton, it's just going to go back to starting material and won't look like anything that happens. And that is what we see at room temperature. And at room temperature, well, it will grab both. The thing we'll actually see from the product is it grabbing the green to go back to the starting material. But in this case, at 100 degrees, it can grab this. And if it grabs this, what we now have is an intermediate that's going to look like this. So we're going to have deprotonated it. And we might be able to form this. We probably are able to form this at room temperature as well. But at room temperature, we can't do the next step. Whereas at 100 degrees, we can do the next step. And that step is pretty much the reverse of the electrophilic aromatic sulfonylation step. These lone pair of electrons can kick into here, causing this lone pair of electrons to go and kick into the positive charge to give us our desulfonylated product plus SO3. Let me actually, I drew SO3, let me draw it in ball and stick formulation. So it gives us SO3. And so this is just the reverse of this mechanism. So here's why we get desulfonylation at 100 degrees and not at 100 degrees, at room temperature. The reason being at 100 degrees, this is a gas, and it bubbles away, and it's gone. And then Le Chatelier's theory is going to take over. Because in Le Chatelier's theory, if you haven't noticed, that's my favorite cop-out answer, Le Chatelier's theory. In Le Chatelier's theorem, if you remove if you move the product from a reaction, you're going to shift the reaction towards the product to regain equilibrium. So at 100 degrees, the SO3 we form in this crazy step is going to bubble away. We're removing it from the system. And then that's going to push to equilibrium, favoring this. Whereas at room temperature, the SO3 does not bubble away, it just stays, and then it can go and it can react in a electrophilic aromatic substitution again. And so then the equilibrium just favors the product by how we push it. Yes?
Is that oxygen supposed to be positive on the SO3?
Oh, that was just a plus, sorry. That was a plus like this.
Okay.
So it's this plus this. I guess it's not, it was really a gratuitous plus, so I apologize. So, there we go, at 100 degrees, the SO3 bubbles away, yeah.
So, how would you get to that product if you had taken the route to do the arrow pushing towards the hydrogen?
Oh, no, so you mean if you do the arrow pushing from here?
Yeah.
We can't, we don't.
Uh,
We don't. It only goes if you take this proton. So, it can only go forward to get this proton. If you take this proton, it's just going to go back to here.
all right.
It's just going to go back to here if you take this proton. Yeah.
On the sulfonylation over on the far
Yeah.
right, is it supposed to be in equilibrium when the water deprotonates it, or is it just
It's acid-base. You know, acid-base is equilibrium. So a sulfonic acid is got a pK of sub-0. When